So this is the start of Process Fundamentals Part 2. In the previous section, we looked at how chemicals partition in the environment, how they move from one phase to the other, from one environmental compartment to the other. In particular, we looked at how pure liquids and pure solids exhibit a vapor pressure, which is the pressure that is measured above a pure liquid or a pure solid. And we also looked at how mixtures of liquids also exert a vapor pressure, and we used Raoult's law to describe what that vapor pressure would be. We also then looked at how chemicals will partition into the aqueous phase by looking at the aqueous solubility, CW-SAT, and we also looked at how Henry's law can be used to describe the linkage between chemicals in the gas phase and in the aqueous phase. So that was all Process Fundamentals Part 1, and what we're going to do now is we're going to add yet another environmental compartment, yet another way in which chemicals can move throughout the environment. So here is our box diagram that we've been going back to time and time again. This should look familiar to you now after having gone through Process Fundamentals 1. We've got the pure liquid or solid phase down at the bottom in yellow, and we have various arrows drawn between that phase and various other phases. We've already covered how pure liquids and solids get into the gas phase, and that vapor pressure, P superscript 0, is used to describe that distribution of chemical between the pure liquid or solid and the gas phase. We've got a linkage between the pure phase and the aqueous phase, water, and that's CW-SAT. And then we've also got the linkage between the aqueous phase and the gas phase, that being the Henry's law, KH. The new compartment that we're adding on this slide is something that we're going to call octanol. And by now you're probably well versed in naming organic chemicals. So oct would mean 8 carbon atoms. You've got the AN in there for an ane, so that would mean that you have all single bonds. And then you have the OL indicating that we have an alcohol. So octanol is our new phase. And you might be wondering, why are we putting octanol on this slide? There's not a lot of octanol out in the environment, certainly not enough to constitute a new separate phase where chemicals can partition into. Well, the reason why we have octanol on this slide will be made more clear later on, but the short of it is that we use octanol as a surrogate for more environmentally relevant media, such as natural organic matter, NOM, which we'll talk about later, biological lipids, which would be the fatty tissue of various organisms, and also we can use octanol to represent other solvents that might be present, not typically natural to the environment, but other solvents that perhaps we've introduced to the environment. So that's why this box is on this slide. And anytime we put a new box on this slide, what we've done is we've created linkages to some of the other boxes. And so sure enough, we have a linkage between this octanol phase and the water phase. That linkage is described by a KOW, capital K indicating an equilibrium constant, OW indicating octanol water. So KW will function very similarly to how KH functions as a linkage between the water and the air. KOW will serve as our way of describing how the chemical partitions between the aqueous phase, the water phase, and octanol. So again, I come back to my little cartoon representation of the world. What I have here in this system is I have the aqueous phase represented by the little V's, the water molecules, and then I have octanol in contact with the water. The octanol, you can see the little molecules I've drawn there. It's basically 8 carbon atoms, as we discussed earlier, with an OH group attached to the first carbon atom. So this could be described as one octanol, or the slang name for it would be N-octanol, the N standing for normal octanol. But if we take octanol and put it in contact with water, the octanol is less dense than water. It's an L-NAPL, so it's going to essentially rise to the top with the more dense water sitting below. If we then introduced, as we will on the next slide, if we then introduce a chemical into this system and allowed the chemical to move throughout the system and partition in this system, some of the chemical will reside in the water phase and some of the chemical will reside in the octanol phase. So the octanol water partition coefficient, or KOW, we defined it on the last slide, but here's the equation that we're going to use to describe KOW. KOW is the ratio of the concentration of the chemical in octanol to the concentration of the chemical in the aqueous phase, or water phase. So KOW is essentially a ratio of different concentrations. And you can think of KOW as being essentially the fraction or proportion of the chemical in these two phases. So if KOW is greater than 1, it means that the concentration in the octanol phase is higher than that in the aqueous phase. And if it's less than 1, then the concentration in the aqueous phase is larger than it is in the octanol phase. Since KOW is a ratio, or it is a fraction where the concentrations in both the numerator and denominator have the same units, the KOW is essentially dimensionless. But in reality, we do remember that it does have different a different basis for the volumes that we're talking about. So here I'm actually not showing the KOW as being dimensionless. It's actually the liters of water divided by the liters of octanol. And sure, those liters cancel out, but I keep in these units because I want to remind ourselves that we are talking about the partitioning of the chemical across those two phases. If C-octanol and seawater were both in units of milligrams per liter, the milligrams are the same basis. They're both the chemical, milligrams of chemical. But the liters are actually referring to two different phases. Liters in the aqueous phase or water phase, and then liters in the octanol phase. So why do we use KOW? Well, as I said earlier, it's useful to use octanol as a surrogate for different environmental media. We can use the KOW to describe how well chemicals partition into other solvents, how it partitions into natural organic matter, NOM, which we'll define later on, and it's useful to describe how chemicals partition into biota, like fish, cells, lipid, etc. KOW is also very closely related to aqueous solubility. So the degree to which a chemical partitions into octanol is, you can think of as being a pure liquid, octanol being pretty close to a pure liquid. How well a chemical partitions into octanol might also be a good descriptor of how well a chemical likes to stay in the pure liquid phase. So you can think of, for some chemicals, many chemicals, the KOW is going to be a good predictor of aqueous solubility, because the aqueous solubility tells us how well a chemical dissolves into water and gets out of the pure liquid phase. So you could imagine that KOW and the aqueous solubility would be inversely related as a result. and we'll see that later on. There's also a huge database of KOW values available. So for just about every single chemical that we would be interested in, there's been someone who's either measured or estimated the KOW value. So even though octanol does not exist out in the environment as a separate phase, it's just very instructive. It tells us a lot about the partitioning of the chemical, and we've got databases of these chemical values for KOW for just about anything we'd be interested in. So how did octanol become the chemical of choice to act as a surrogate? Well, you've seen the chemical structure of octanol. You know the chemical structure based upon the name octanol, 8 carbon atoms in a chain, all single bonds, no branching off of that chain, and then there's an alcohol group attached to the first carbon. Well, octanol has both what we say hydrophobic, fear of water behavior, and hydrophilic, love of water behavior. And it really depends upon what end of the molecule you're talking about. So here in this diagram I've got benzene, the very familiar benzene, and you can see that benzene has partitioned into octanol. So you see that the benzene is surrounded by lots of octanol molecules. And in particular, the end of the molecule that has decided to surround the benzene is the non-polar chain of octanol. So you can see the carbon-carbon single bonds in the chain. You can see them surrounding the octanol, I should say the benzene molecule. And the reason why this happens is because the benzene molecule is very non-polar. It's just an aromatic ring of carbon atoms with one hydrogen atom bound to each carbon. There's essentially no polarity there. There's no oxygen groups or nitrogen groups to impart polarity. So it's very non-polar. And so it's the non-polar chain of the octanol molecule, which is the hydrophobic end of the molecule. And it's going to surround and essentially stabilize the benzene through van der Waals forces. These are the forces that exist between all molecules. So in the bottom diagram, what we have is, once again, octanol, but now the chemical that is immersed in the octanol is water, H2O. And as you know, water is very polar. It's got the oxygen-hydrogen bond, which is a very polar bond. It also can form hydrogen bonds if there's a suitable oxygen atom on the solvent molecule, which there is in the case of octanol. And so what you see now is that the water molecule is surrounded by octanol, but the difference here is that it's the OH group of the octanol that is surrounding the water molecule. It's the oxygen group in particular that stabilizes the hydrogen atom of water, and it's the hydrogen atom of octanol that can stabilize the oxygen atom of the water. So you have both van der Waals forces and hydrogen bonding that are able to stabilize the water molecule. And so this is the end of the octanol molecule, which is hydrophilic. Hydrophilic meaning love of water. So octanol is interesting in the sense that it has the ability to stabilize both very nonpolar molecules like benzene and also very polar molecules like water. And as a result, octanol is said to be amphiphilic, so it's able to have both hydrophobic and hydrophilic qualities. So octanol, just turns out, is a good surrogate because a lot of the environmental media that we're interested in, like NOM or lipid, has the same amphiphilic quality to it. So octanol, just for whatever reason, just wound up being the solvent of choice to sort of study how chemicals partition into these environmental media. Here's a chart. It's a chart that I've shown many times before, or a similar chart to one that I've shown before. Now, instead of vapor pressure or solubility on the x-axis, now we've got the octanol water partition coefficient, KOW. The units, as I said before, are dimensionless, so it's the same here. And basically what we have is the series of chemicals that I've shown all these other times before. And let's focus in on benzene, the alkylated benzene bar at the top. So you can see benzene has a KOW, and since this is a log scale, has a KOW of about 10.22, 10 to the 2.2, I should say, 10 to the 2.2. So it's got a KOW of just over 100. And you can see as we increase the alkyl chain on the benzene group, as we add more carbon chain to the benzene molecule, we increase the KOW. So what that means is we increase the KOW, what we're doing is we're essentially increasing the amount of chemical that would partition into the octanol phase at the expense of the aqueous phase. So as we add those nonpolar groups to the benzene molecule, more and more of the chemical will want to flee to the octanol phase, will want to be partitioning into the octanol phase. The same thing holds true for the PAHs down at the bottom. You can see we've got naphthalene with a KOW of about 10 to the 3.5. And as we increase the number of benzene rings within the PAH molecule, you can see that what we're doing is we're vastly increasing the value of KOW, meaning that it will want to partition more and more into the octanol phase. So, again, if I take my water and I put it into contact with octanol, the one thing that we have to keep in mind is that when we do this, is that because octanol is amphiphilic in nature, some water will actually get into the octanol phase. Some water will actually partition into that octanol phase. You can see I've got a few of the little V's, which represent the water molecules. You can see that they're up in the octanol phase. And at equilibrium, if we've got N-octanol, there'll be roughly one water molecule for every 4 octanol molecules. So octanol is that good of a solvent for polar molecules that quite a bit of water actually gets into the octanol phase. The converse is not true, however. We don't see much octanol getting into the water phase. There's roughly 8 octanol molecules for every 100,000 water molecules in the aqueous phase. So if we let these two solvents come into equilibrium with each other, we have to remember that the octanol actually will wind up with quite a bit of water in it, but the same is not true for water. So when these two solvents are put into contact with each other and allowed to come to equilibrium, we say that the octanol is now water saturated. So it's water saturated octanol. It's still mostly octanol, but it's saturated with water. And what this does is it actually changes the molar volume of the octanol. Molar volume meaning the liters of space occupied by 1 mole of material. This is helpful when converting mole fractions to concentrations, as we did earlier for the CW-SAT calculation. So the molar volume of pure octanol is 0.16 liters per mole at 25 degrees C, whereas water-saturated octanol is significantly less than that, 0.12 liters per mole. So now that we've gotten the octanol and water partitioning out of the way, in terms of how much water will partition into the octanol and how much octanol will partition into the water, as we saw in the previous slide, far more water gets into the octanol phase than octanol gets into the water phase. But now that we've kind of covered that and gotten that out of the way, what we can do now is introduce a chemical. And you can see my cartoon very similar to the previous slide, except now I have the black circles which represent the chemical of concern. So this is our organic chemical. Could be benzene, could be naphthalene, could be PCE, could be whatever. So we're going to introduce the chemical, and when we do these experiments, which we've done in my lab many times, what we do is we basically add the chemical to the water. We'll inject it into the water phase via a syringe. We'll basically dip the syringe through the octanol into the water and inject the chemical into the water, and then we'll wait. We'll wait 24, 48 hours to let the chemical partition throughout the system. And what will happen is that the chemical starts off in the water, and eventually some of it will partition. It'll move up into the octanol. It will partition into the octanol until we reach a state of equilibrium, where the rate of movement out of the octanol into the water is equal to the rate of movement from the water to the octanol. So we know that once we reach equilibrium, the way we describe it is with our approach that we've been using time and time again, is we equate the chemical potentials in both the octanol and water phases, and that's akin to equating the fugacities, or the fleeing potentials, or the fleeing ability of the chemical in the octanol and in the water phase. We defined the fugacity in the water phase as being the vapor pressure of the pure liquid times the mole fraction in the water phase times the activity coefficient in the water phase. And what we're going to do now is we're going to define the fugacity in the octanol phase very similarly to that. We're going to define it as the vapor pressure in the pure liquid from the pure liquid phase exerted by the pure liquid phase times the mole fraction in the octanol phase times the activity correction for the octanol phase. We're then going to swap out the mole fractions for concentrations, because that's what we're more used to dealing with, and we're also going to cancel out the vapor pressures because they appear on both sides of the equation. When we swap out the mole fractions, we wind up with a concentration in the octanol phase times the molar volume in the octanol phase on the left-hand side of the equation. And on the right-hand side, we wind up with the concentration in water times the molar volume of water. So, what we're going to do now is we're going to write out an equilibrium equation, which is basically the KOW, capital KOW, so it's the equilibrium constant between the octanol and water phase. We're going to say that that's equal to the concentration in the octanol phase divided by the concentration in water. So C octanol over C water. And this is very, very similar to how we do Henry's law, where we look at KH as being the partial pressure divided by the concentration in water. This is just, instead, it's the concentration in octanol divided by the concentration in water. So that's how we define our KOW. And then what we can do is we can write out the KOW in an equivalent way using the line right above that where we equated the fugacities. We can swap out C octanol for CW by simply writing it as the ratio of the activity coefficients in the water phase to the activity coefficient in the octanol phase, that ratio, times the ratio of the molar volumes of the water and the octanol phases. So if you know the molar volumes, which we do just about for everything, and if you know the activity coefficients, you can calculate the KOW. Or if you know the KOW and you know one of the activity coefficients, you can get the other. So as we go through the derivation for KOW, one thing you might be wondering is how does KOW relate to something like the aqueous solubility? If you remember, aqueous solubility was something that described how the chemical goes from the pure liquid phase to the aqueous phase. And the KOW is a descriptor of how well the chemical partitions between octanol, which is an organic liquid, and the aqueous phase. So they're in some ways somewhat very similar, in that the chemical is partitioning between an organic liquid and the aqueous phase. So, in fact, yes, there is a relationship between the KOW and the aqueous solubility. They do trend with each other. And as the KOW gets larger, the CW sat, the aqueous solubility, gets smaller. And that's because the chemical does not want to be in the aqueous phase. As the KOW gets larger and larger, the concentration in water decreases, and therefore the CW sat will also decrease. In other words, the chemical does not want to be in the aqueous phase. It would rather be in either octanol or rather be in the pure liquid phase. And that's really what this plot shows. It shows a bunch of data for just a tremendous number of different chemicals. The symbols represent different classes of chemicals. I would say what we could do is we could focus on the filled-in circles. Those are our substituted benzenes. So this is, benzene, xylene, toluene, BTEX compounds. And you can see they fall on a pretty good line. There's reference lines shown on this plot, 4 of them, in fact. Each line corresponds to a different activity coefficient for the octanol phase. So it goes from the activity coefficient of 1 all the way down to 1,000. And you can see that most of the data, if not all of the data, close to all of the data, falls between an activity coefficient in the octanol phase of 1 and about 100, with a few outliers. Now, what is that about? Well, if we recall the definition for KOW on the previous slide, it was the ratio of the concentration in the octanol phase to the water phase. And equivalently, that could be written in terms of the activity coefficient in water divided by the activity coefficient in octanol times the ratios of the molar volumes. That's what's shown on the top line on this slide, the first equation there. If we assume for a minute that the activity coefficient in water is equal to the activity coefficient in water at saturation, and if you remember from our previous discussion that was a decent assumption for molecules that did not have a very large aqueous solubility, that was a pretty good assumption. If we make that assumption, and if we simply take the logarithm of the first equation shown at the top, we end up with log KOW is equal to log of the activity correction or activity coefficient in water at saturation, gamma subscript W superscript sat, times the molar volume in water minus log of the activity coefficient in the octanol phase times the molar volume of the octanol phase. Just taking the logarithm of the equation above. And then if we simply make the substitution that the activity coefficient in water at saturation times the molar volume of water, that is actually equal to, by definition, CW sat. We'll make that substitution. You can see that there's a relationship between KOW and CW sat. Log KOW is equal to minus log CW sat with a correction. And that correction is minus log activity coefficient in octanol times the molar volume of octanol. So if we were to plot log KOW versus the logarithm of CW sat, we would expect a slope of exactly -1 because of the minus sign, indicating an inverse relationship. And we would expect an intercept of that line of log of the gamma octanol times the molar volume of octanol. And so what you see plotted here is, in fact, a slope of very close to -1. And the only reason why there isn't, the only reason why all the data doesn't fall on the same line is that we've got different intercepts here, where each line shown on this plot, each diagonal line corresponds to a different value for the gamma octanol phase. So basically the relationship is a pretty good one, and it's what we would expect. based upon our understanding of KOW and the CW sat, the aqueous solubility.